much as the introduction said, I've been working with all the fields of the economy of the sea, and it is for me a pleasure to be here with this distinct audience moderating this first panel. As I will have also a talk during the afternoon, I will not be long with this introduction. You have the word now.
Well, thank you very much, Mr. Ambassador, Mrs. Patrícia Gouveia, Mr. António Sarmento. In my name and the name of the company, I thank you very much for this invitation, in which what I tried to share with you is basically our experience in terms of the offshore wind. As you may know, our company belongs to EDP Group. We are 77% detained by EDP, and the balance is listed internationally. So we are market leader, world market leader in wind onshore. We are number 3 in the world, which is today a very green and competitive industry. And the question that we may ask is, why are we also involved in offshore? And I think this should perhaps be the, let me just see if I can. And why are we also in offshore? If today, as you can see by there, wind onshore is clearly a competitive industry, we compete without without classical thermal power plants. The only technology which is more competitive than wind onshore is today hydro. So why are we going to wind offshore if wind offshore is not competitive today? And we know today that a few years ago it was enough to be green, and everybody was very happy with that. Today, besides being green, most of the people require also that we are not expensive. So when you look at this, why are you also in offshore? Our point is that although today wind offshore is still expensive technology, there are reasons that in certain countries to grow ahead with offshore. And why? I would say first point, which is very important. Wind offshore makes sense is first in areas and countries in which wind onshore is not available. And this is what? Not available means what? Either because the countries are overpopulated, cases of Japan, cases of UK, or because, although not being overpopulated, is a country with very heavily or homogeneously populated, case of France, in which people are like very much the green products, but not in their backyards, this NIMBYs effect, which is very important. So there are many countries in which it's not possible to develop wind onshore because of social or demographic issues. On the other hand, there are places in which most of the important places in wind onshore have already been occupied, or there are grid connections. So, firstly, there are places in which it makes sense to develop wind offshore. Second idea is that wind offshore may be a way of creating a cluster. We cannot forget that today in Europe, because Europe was the pioneer in terms of onshore, Europe is still the market leader in terms of industry. When we speak about the market leaders, we speak about companies like Vestas, you can speak about companies like Gamesa. So in the top 5, you have 3 or 4 European companies. And this can always happen in offshore, in which I will comment later on, the national component can be huge. But there is a third component. So difficult to develop onshore, possibility to create an industrial cluster, and the third reason to develop offshore must be a belief that the technical progress will move the costs down. And we think they will. The costs, and I have here our internal projections. We are not being aggressive here. We may expect really easily reductions of about 15% during the next decade. And I'm not being really optimistic on that. This is perfectly sensible. And when we think that onshore, which everybody thinks it's a very stable industry, the reduction in costs was about, I just read a report yesterday, in the last 5 years, the reduction in costs in onshore was about 60% on cost per megawatt hour produced. So I would say that there is a strong expectations of reduction of the costs. How? Bigger turbines, more evolution in terms of the technical area, in terms of the substructures, important progress in terms of logistics. So I would believe that because of this, the odds that we'll be able to reduce the costs, not likely to the levels of onshore, but to reduce strongly the costs and make sense in countries in which it's not very easily to develop much more the traditional, the more mature areas, I think they are there. And this is why we think, although being a market leader in onshore, we think that we should move to offshore because it's a sector in which we believe and because we have, of course, a comparative advantage. It's not the same, offshore is not the same as onshore, but there are things which are similar, I would say, wind assessment, the electrical part, the electrical components are similar, so we leverage on those comparative advantages we have. Of course, there are areas which we don't know, which we know less, namely in what concerns the logistics or when we speak about floating platforms, but I would say that with that mix, we decided to go to offshore. And go where? Basically, we are in 3 places, and I would just comment briefly. In the case of UK, we are together with Repsol, which is a main Spanish company. We are in the process of tendering to 2 projects in UK. In the next tender that will be held in December, we are in Edinburgh with the team since 2009. So the high load factors. It was a difficult process to develop, but high load factors, the authorizations today are obtained, and we expect we'll do our best to be competitive there. France is not a competition. We won already the competition together with GDF, so we are developing 2 projects in France, one in Normandy, the other one in Vendée. In this case, everything, from the point of view of economic model and interconnections, this is done, so we are developing that. In that country, we are introducing 8 megawatt turbines, and finally in Portugal, which is important for this audience, we have launched, in terms of EDQ Group, a pilot of 2 megawatts of a floating platform near Povo de Varzim. It proves the cost of the investments, of course, were high, but it was a prototype, 2 megawatts, as we believe. It's not the optimal scale. It proved that it works. Even with very bad weather, as you remember in the last winter, it continued to produce power. So what we are moving now into something in the middle between the full industrial scale and a prototype, which is this 24 to 28 megawatts projects that we expect to launch near Viana do Castelo. Which this project is going to be supported by European Union through NER 300 project, and we are in the process of developing it. It's not an easy project, as you may believe, but we are confident and doing our best to do it. So, 2 projects from more traditional, if you say you can qualify the traditional offshore in UK and in France. In France, we began later on, but it's moving together with GDF, Gaz France. In UK, we are confident that we'll be able to be competitive. Portugal, we are in this area of mid-experience between prototype and the full scale. One important thing, the value add and technology. We are speaking here in Portugal of about 50% of national value added, namely the metal issue, the components. It's interesting that the technology is from a company in which we participate, which is with French and US intelligence and technology, which is Principal Power, which is written there, and so we are confident. So this, you see, it's just an interesting project that if we work successful here and we prove that with this 28 megawatts the process is viable, we think that internationally there will be a very strong market in countries in which, as I told you, offshore is needed. Offshore with deep waters. With deep waters is over 50 meters. I would say that in countries like Japan or in certain areas of France can be a solution. The other 2 are much shallow waters, less than 50 meters. Here you are speaking about a different league, but it's a challenge. Have been in the beginning. I told that one of the reasons to develop this is that we have to contribute to define partnerships. So this way of producing power is still expensive. We should not deny the facts, but can improve and can contribute to defining industrial clusters. And this is a preoccupation that we have everywhere where we are. So either in England or in France, and of course in Portugal, one of our worries and our main objectives is at the same time we produce electricity, we should contribute to create clusters. In England, working with established producers. In France, Arriva is going to make 2 new factories to support this factory. In Portugal, we are in the process of doing the same, and this for us is nothing new. A few years ago, and the time runs shortly, in the 2005 or 2006, we were awarded in the consortium a big project of development onshore, and we were able to partner with a German company, Enercom, which built industrial cluster in Viana do Castelo, by chance, in which works with 3 factories, and most of the production is exported again. With this, besides doing business which we think are profitable with risks controlled, we try to contribute wherever we are to the development of the local industry. Finally, I would, from being an economist, I would like to speak a bit about the risks. Of course, these are projects. It's easier to make a solar or an onshore business than an offshore one. The risks are bigger. Namely, just think that in an offshore, if you have bad weather, we can be paying for a ship to transport the turbines for a few days, and it's very expensive, so the risks are bigger. And we are prepared to take the risks. We are prepared to take the risks that we control. What we think is that the regulatory systems that we are created should not give to the should not put on the side of the promoters risks that they cannot control. For instance, making a project, an offshore project, expecting to sell power in the spot market is a complete nonsense. We are speaking about 4 million euros per megawatt maximum, on average. 4 million euros per megawatt project, very capital intensive. We must have certainty about the incomes if we are able to produce. How can we have certain doing long-term agreements on a tender basis? This is the proper way. So we have competition, but ex-ante competition and long-term. So first, the system must be based on long-term system. Second, it's important that the system does not give special rights to the incumbent companies. For instance, if I am obliged to make a private long-term agreement, I will be in the worse situation than an incumbent that has distribution with them. And finally, I would say that the risk of interconnection, I would say, should not be taken by us, by us promoters, because really it's a risk they cannot control. So meaning that, and what's the advantage of putting the risk on the right side? The advantage of putting the risks on the right side means that when I bid for a long-term agreement, I have a lower cost of capital. And if I have a lower cost of capital, I can provide a cheaper funding, cheaper projects, and in the end of the day, cheaper price of power. The case of France, it's a good case. I'm not going to develop this, but it's a good case in which the things were made on a very sensible way. So we tender, competition ex-ante, we just began to invest a lot after winning. And it's important, network was connected, so very clear method of allocation. So I would say, it's not the moment to discuss the French one, but I'll give you an example that doing the things like that, transparent, putting the risks on the right place, I would say are good for everybody. So in the end of the day, I would say that we should not be obsessed by the fact that offshore is more expensive today. There are reasons to develop offshore in places where it makes sense, in terms of, because of the lack of alternatives, also because industrial case and believing that will be a decrease in prices. We think that the decrease in costs will happen, provided there is a scale, and we are, on an international basis, in Portugal, of course, but also in France and UK, prepared to continue to develop. Thank you very much.
Thank you very much. I'd like to thank the organizers for inviting me here. This is my first time to Portugal, and it's been a delightful trip so far. So there's a couple of acronyms in my talk that you'll be hearing. One is NEMREC. NEMREC is the way we talk about the Northwest National Marine Renewable Energy Center. That's a bit of a mouthful. And as I was introduced, I'm the director of that center. So in 2008, the U.S. Department of Energy put out an announcement for up to 3 marine energy centers whose goal would be to look at the technology challenges, the environmental challenges, social challenges, to do research that would help advance these technologies and help inform regulators and educate students. And so as a result of that funding call, the Southeast Center was founded at Florida Atlantic University, and they're focused on extracting energy from the Gulf Stream and a little bit of work in ocean thermal. The Hawaiian Center was formed, and they work very closely with the Navy at the Marine Corps base at Kaneohe Bay. There's a test facility there for wave energy devices, and they do ocean thermal energy as well. And then the third center is our center, the NEMREC Center, which is a collaboration between Oregon State University and University of Washington. Initially, those 2 universities divided up the technology sectors, with Oregon State focused on wave energy and University of Washington focused on tidal. Since that time, those divisions have blurred quite a bit, and it really is quite a strong collaboration. And just last month, we announced that we've added University of Alaska Fairbanks to the mix. So I'm going to tell you what these 3 universities have been doing together, working with the industry to try and address the challenges of moving wave energy, tidal energy, and some work we've done recently in offshore wind out into the ocean and making it a viable part of our renewable energy portfolio. So as I mentioned, our mission is very much focused on applied research, trying to work with industry, trying to look at not only the engineering side of the house, but environmental and social challenges. And we work fairly closely with regulators as we're putting projects in the water, trying to help them understand what the impacts of these technologies are. So when Department of Energy first formed our center, they gave us 5 or 6 different project objectives. And as you'll notice, the first one was to develop an integrated set of test facilities. And that project has really grown quite a lot, where it's really developed into its own piece that sits alongside the research pieces. As I mentioned, our research fits into several sides of the house, and I don't have enough time today to go into the in-depth the kind of research we do, but if you look, we have a fairly broad team that spans engineering and every engineering discipline except nuclear. We have nuclear engineering. We can't figure out how to bring them in, but we have mechanical, chemical, electrical, ocean engineering, industrial engineering, so very broad. At Oregon State, we've got a very strong School of Public Policy, and we have some of those faculty engaged. We have marine biologists and oceanographers, so you see a very broad swath of the different types of research aspects covered, in addition to producing graduate students in all of these areas. So I mentioned that the testing side of our house had grown quite a lot. And my counterpart at University of Washington, Brian Pelagi, and I got together and talked about how do we group our testing efforts in a way that would be recognizable to the world, because we really do attract developers from around the world who come and work with our faculty. So I think in Europe, most people know about the European Marine Energy Center, or EMEC. They're up in Orkney, Scotland, and they've got a wonderful test facility up there. So we decided we would be the Pacific Marine Energy Center, or PMEC, and that would help people globally understand our aspirations, if not our current capabilities. And so just as someone would say, I'm going to go test a device at EMEC, just from that statement, you don't know whether they're a wave developer or a tidal developer, or whether they're doing something at scale or in the full ocean energy environment. That's what we have with PMEC. We have at our campuses, so if you look at the At the inshore area there on the map, Oregon State University has some wonderful scaled wave tanks, and our partners at University of Washington have some the facilities at the Harris Hydraulic Lab as well. Then people move out into the open ocean, and you'll see my map needs to be updated because all I'm showing here are Oregon and Washington, and my Alaska announcement is so recent that we don't have the Alaska facilities on here yet, but I'll tell you a little bit about what's going on there. So focusing on what our testing capabilities are, and this is one of the prime areas that developers think about us as a resource, is with our testing capabilities, although we do get involved into collaborative research projects. So on the far left of this picture, you see our linear test bed. Oregon State University has the highest power research lab of any university in the country, and what people can do there is test the generator capabilities of their devices. In the middle there, the other 4 pictures there, you're seeing our wave tanks. We have 2 wave tanks that people have used. The one in the middle on the bottom is our large wave flume, which is a little over 100 meters long, and it's about 5 meters deep and about 3 meters wide. We've been testing devices there that are about 1/15th scale. And then on the far right of the picture, you'll see our tsunami basin or directional wave basin. And we're testing an array in that picture. That facility is about 40 by 60 meters, and it's got a wave generator which consists of 29 different paddles. So you can generate all different kinds of wave environments that are helpful for developers to understand what their device does in some very realistic scenarios. One of the things developers will do is test the resilience of their device within a 100-year storm scenario. So after people go and test in the tanks, then they want to go out to the water. And here's an example of where the collaboration between University of Washington and Oregon State has blurred the lines, and it's not so divided tidal and wave any longer. We hadn't initially anticipated that Lake Washington, right near University of Washington, would be a great place to do some scaled testing. And so Acilla Power tested a scaled device with our Washington team. And they're looking toward, right now I think they're going to a place in New Hampshire, but they have their eyes on coming down and testing with us off the coast of Oregon in a full-scale wave environment. Speaking of the full-scale wave environment, the first thing we did in developing our testing facilities is develop a site there depicted by the star in the territorial sea. That dotted line there in the middle of the water is the dividing line between the territorial sea, which is 3 nautical miles from shore, and the outer continental shelf that is controlled by the federal agencies. And our idea there, based on extensive community outreach, was that the Oregon community at that point was not interested in having a permanent test site. They wanted to have something that was mobile, that could go to where developers needed to use it, that wouldn't be out in our waters all the time. And so the concept was to develop a mobile ocean test berth. That's on the picture on the right, you have something that looks a little bit like a ship. That's our mobile ocean test berth, which we call the Ocean Sentinel. And you can see a wave energy converter connected to the Ocean Sentinel through an umbilical cord. So that was our first concept for testing. We did testing in that way. The device in the near part of your picture on the left is the WetNZ device from New Zealand, and it's connected through an umbilical cord to the Ocean Sentinel, which you see in the far part of that picture on the right. And this kind of testing configuration works quite well if your device is producing up to 100 kilowatts. So it's a way that you can get out in the full-scale wave environment and do some scaled testing with respect to the electricity, not with respect to the wave environment. And so that was a place for WetNZ to test initially. We've had other people who have been interested. Unfortunately, in the US right now, there hasn't been the funding. That's been the big gap, is the developers haven't had the funds to continue to come into our facilities, but the facility is up and available. So based on that initial experience, I did mention scaled with respect to electricity. we were hearing a lot from the developers that they wanted to have a facility like PMEC that was connected to the grid with the full wave environment. And so we started working on the Pacific Marine Energy Center South Energy Test Site. This is a plan for a grid-connected facility. We will have 4 berths. Each berth will have its own cable. Each berth will be capable of testing small arrays. So in that respect, we're different from PMEC. They test single devices. And so small arrays being 3, 5 devices, something along those lines. And we've been very active in the permitting activities toward this site. We are trying to get it so it's pre-permitted for virtually any device that's out there right now. I put it that way because somebody could come up with some idea that we wouldn't have thought of. It might take a little bit more work with the regulators. But if everything goes as planned, we expect to have our permits by the end of 2016 or the beginning of 2017. And we're hoping that sometime in that time frame, U.S. Department of Energy will announce full funding that we'll be able to go after to then complete this site. And that site, just for your point of reference, is a little bit south of that other site I mentioned. That's why we call it the South Energy Test Site. It's off the coast of Newport, Oregon, which is directly west of our university. So I mentioned a little bit, one of the other things that we do for developers and for the industry and for the regulators is to look at environmental effects. And I don't have enough time today to go in depth into our environmental work, but we've started the discussion with the regulators with looking at all the different things that you might have happen when you put a device in the water. What part of the environment and the ecosystem are you affecting? What kind of organisms are you affecting? And it goes everything from the birds that might be affected from the lights on these devices and their migration patterns, all the way down to the things that live in the sandy bottom. And so one of the things that happens when our discussion with the regulators, since we're a university, is they'll say, hey, we don't know anything about the green sturgeon in this area. Would you like to do a research project on green sturgeon? And since we're faculty and graduate students, our natural response is, yes, we'd love to do a research project on green sturgeon. And if this conversation continues in that way, next thing you know, your permitting, your environmental monitoring costs are millions of dollars for the projects. So we say, okay, we can't have that conversation. Instead, we need to say, since we're a university, we can do lots of different research projects that can answer your questions, but we need to prioritize them. What are the most critical questions that we need to know to get your devices in the water? And as we answer questions, let's take those issues off the table so that the environmental monitoring costs are not prohibitive. And it's been a very productive conversation with the regulators with an eye toward making environmental monitoring at our facility very cost effective for developers and answering the questions that will take things off the table as we move forward so that we can really make this an affordable industry. So the kind of work we've done, one of the things has been, one of the priority areas has been acoustics. And one of the faculty at our Hatfield Marine Science Center at the coast has developed an acoustic lander. He's left it out at our sites for a year to characterize baseline so that when we put devices in the water, we know how loud they are. Another piece of equipment that's been developed by our University of Washington partners is an ROV-based deployment system that has a very expansive suite of environmental monitoring devices on that system. It's called the AMP, the Adaptive Monitoring jet lag there. I forget what the P stands for, sorry for that, but we call it the AMP, and it can do acoustics. It's got some GoPro cameras on board, so you can get a variety of information about what's happening in your deployment. Another thing that our Washington partners do is they support turbine testing. They were up in Igiugig, Alaska about a month ago with the ORPC deployment, working on acoustic monitoring, helping understand what was going on the environmental side of things. And in terms of looking at the environmental interactions, we've also been working on supporting offshore wind deployments, looking at bat and bird detection. How do you decide if there's bat and bird detections around wind turbines? On terrestrial turbines, often you find the remnants of a bird or a bat by the turbine, but you're not going to have that happen in the ocean. So how do we quantify what kind of interactions take place? And lastly, I mentioned that we expanded to Alaska. Here's a picture of our Alaskan partners. They have a site on the Tanana River where they are working to counteract the effects of debris. In the springtime, you have very large logs being washed down this river as you have the melt from the winter. And those logs would destroy a turbine that you would put in the water. And they've developed a very nice system for dealing with that debris, counteracting the debris, and we've asked them to join our team to help us understand how we might do similar things in the wave environment and in the estuary tidal environment. They're also involved in a project in Yakutat, Alaska, and as you'll hear, I expect from one of my colleagues here, Bill Staby, who's interested in testing in Oregon and in Alaska. This is another place where we can have good collaborations because we're dealing with the same people who want to come test with both of us. And so on that, I'll conclude with our continuing role is doing more of the same. We look for ways that our research can help the industry. We look for ways that we can collaborate. We try to provide test facilities that help industry understand their devices and are busy working on trying to create the grid-connected test facility that I mentioned, which we anticipate will be an excellent resource not only for the U.S., but globally. And with that, I'll thank you.
Thank you very much. As you can hear me here. Ambassador Sherman, Dr. Sarmento, and our friends at the Gulbenkian Foundation, thank you very much for organizing this conference. It's truly an honor to be here, representing not only my company, but the U.S. Just so that you know, I guess, Ambassador Sherman, you're from Massachusetts as well. Many of you may know that the largest concentration of the Portuguese community is centered in Massachusetts and Rhode Island, as well as the Cape Verdean community, which when we get a little bit further into my presentation, you'll understand why I'm talking about that. The title of my presentation today is Seawater Desalination, a Promising Commercial Application for Wave Energy. As more of a startup guy, I'm certainly not an engineer, I'm very, very concerned with where is the earliest commercial application for some of these new technologies that are being developed. And as you'll see as I go through the presentation, that's and our particular focus is in seawater desalination, applying wave power for that. So just a quick introduction to our company. The company was founded in 2007. We are funded primarily by the U.S. Department of Energy over the last 5 or 6 years. We also have a series of private investors that are of a very special kind, which I'll explain also a little bit, part of the reason why we've positioned our company in a particular way. We're supported by, at present, a group of very, very talented engineers and business development people that numbers 10. We're also supported by a technical partner network that includes companies that are familiar to you, probably Parker Hannifin and ABB. We recently, as a company, expanded from Boston by establishing our first European Union subsidiary in Ireland. We have one employee there as well. And we've also established a subsidiary in South Africa, which is one of the areas where we have been working for quite a long time, developing some business related to seawater desalination. So any good sort of business case begins with a problem statement. And so the problem statement really has to do with the world water crisis that we're hoping to be, a partial solution to at least. Over 1 billion people on the planet don't have access to sufficient supplies of fresh water every day. It has a huge impact on the health and welfare of millions of people around the world. In fact, several million a year die from the direct effects of lack of water. But the indirect effects on economies, on education, on even women's rights, for example, are huge. And so this is a big, big problem that's getting only worse, particularly when you expect that there will be 2 billion more people on the planet by 2050. And certainly climate change doesn't really help the situation at all, particularly when it comes to water and food-related issues. So, as you probably know, 70% of the Earth's surface is covered with water. However, 97% of that 70% is all salt water, so it's unfit for human consumption or for use in agricultural crops. And then a further 2% of that is tied up in glaciers and in the North and South Pole, frozen fresh water. So there's only 1% of all the water supplies on the world that are appropriate for use by human beings and for agricultural purposes. So we asked ourselves, what if you could do something to harness the ocean effectively to essentially supply the gap in water that currently exists? And so basically, what we've done is developed a wave-driven desalination system, which its primary value proposition is that it can be set up very, very quickly, supply water very cost effectively, and does not require a connection to an electrical grid. Traditional desalination systems, which use very mature technologies, however, are very, very big energy hogs. And so therefore, they rely on having a robust grid connection in order to operate. In the target markets where we're focused, and I'll describe a little bit more about that, of what they are, they cannot afford these large infrastructure projects, in other words, to develop the electrical generation and transmission capacity in order to support these traditional desal systems. So when our system comes along, it actually represents a very, very attractive solution for them. Another benefit, of course, is that as in Cape Verde, as you'll see in a minute, much of the sort of distributed desalination work is currently done by diesel generators. And therefore, an added benefit is by using a renewable energy resource to drive these desalination systems, you're avoiding the additional use of fossil fuels. So this next after a problem statement, you say, well, how big is the potential marketplace? Is it worth pursuing? All of the countries that are mentioned here by name are areas where we have been working more or less to develop relationships and, in some cases, projects. The areas where we have initially focused are in South Africa and Cape Verde, where both countries have huge deficiencies of fresh water and a propensity to use our particular system as a solution. How this map was created was really quite simple. It's 3 GIS maps that are layered on top of each other. First and foremost, of course, is areas of the world where there are severe water shortages. Second is areas of the world where they have weak or non-existent electrical grids. And then third and finally is areas of the world where there's very attractive wave resources. So when you lay those on top of each other, that's how you get this particular map. One particular area is missing. We have not done much business development work in Southeast Asia, but Indonesia is a huge potential market for us with very severe water issues. So we have actually tested most of the components, particularly the wave energy converter, at full scale in a series of tests that took place in 2012 and 2013 in North Carolina. Off the Outer Banks and in cooperation with the U.S. Army Corps of Engineers. The technology for wave energy conversion that we've developed is a bottom-mounted hinged flap. They're called oscillating wave surge converters. 2 other companies in the world are developing very similar types of wave energy converters, Aquamarine Power and AW Energy. I understand AW has done some testing here in Portugal. They're very, very simple devices. They tend to be deployed very close to shore, which has certain advantages. And another key advantage of this particular technology is when a storm comes along, they're naturally able to shed excess energy. There's no floating components with this that need to be secured. you might see some wheels that would sort of confuse you a little bit. You'd say, well, why are there wheels on this thing? Well, that has a lot to do with our philosophy, our design philosophy. You have to understand who it is that you're designing a particular technology for. So one of the major differences between ourselves and the other two companies I mentioned that are developing these hinged flap devices is that ours is much, much, much smaller. And that is primarily because in these developing countries that I've just highlighted in the previous slide, there isn't a whole lot of infrastructure available to deploy these devices. There isn't a whole lot of, shall we say, well-trained workforce. So to solve that particular problem, the small issue essentially allows you to use pretty much off-the-shelf components, which can be readily accessed and readily switched in and out when repairs are required. The wheel aspect of it has to do with actually launching whenever possible the device from the beach instead of having to have, again, special purpose vessels that are on hand and very, very expensive in order to actually deploy them. So that's a very important component of, again, commercializing any technology is really who is it pointed at, and is it appropriate for them in the actual taking into account the infrastructure that might be present there. So what I'm going to do now is describe the two projects that we're doing. We're proposing to do two pilot scale projects. Actually what it is, they're components, a full-scale component or a building block of the wave-driven desalination system that we're going to be deploying hopefully widely around the world. As Belinda mentioned, Oregon is a good spot for wave energy testing. However, the nets and the sets facilities that they have are deep water facilities, whereas we require shallow water. Roughly 7 to 8 meters of water is where we deploy, which has its own challenges being close to shore, but nevertheless is one of the advantages. And the advantage basically is you're closer to shore, so less of the capital cost is tied up in the infrastructure required to get energy from the wave energy converter onshore to where it's used to essentially power an electric plant or a desalination plant. So this project will also be under a specific permitting regime run by the U.S. Army Corps of Engineers. It will allow us to do a demonstration for up to 1 year, which is all that we require. The configuration of the test program is essentially two wave energy converters, one running dedicated to running a containerized electric generating plant, and the other devoted to running our Wave 2.0, which is a trademark name that we use for the desalination unit. The benefits of this system and what we hope to prove during the test program basically is that we're going to be able to drive this whole system using simply pressurized seawater and pressurized fresh water. Fresh water driving the electric plant in a closed loop system, and seawater driving the desalination plant in an open loop system. There's no chemicals that are going to be used in this process. The brine in this particular situation will be fully diluted before it's discharged back to sea, so there should be no sort of chemical impact of the project. And finally, there's another benefit of these bottom-mounted devices is there's really no mooring lines that can be sometimes very difficult to deal with. So these are just a couple of slides. This is where in Oregon this is. If you're familiar with Oregon, where the Columbia River enters the Pacific Ocean, right around the corner is where Camp Rylea is. It is a Oregon National Guard facility. And the reason that they're interested in working with us has to do with another potential commercial application of wave energy converters, particularly small ones, is in disaster relief situations. Oregon, off the Oregon coast, is an extremely active geological zone. They're expecting eventually to have a large earthquake and a resultant tsunami. And Camp Rilea is meant to be this recovery area where people will be fed and housed post-tsunami, if you will. So they're very, very interested in our system, particularly in how quickly it can be set up after such an event and begin to be producing electricity and fresh water in order to support a population that's mobile at that point. This is just a picture from above that shows the box essentially where we will be looking for an ideal spot to deploy the device. This essentially shows that the transition area is basically 300 meters from behind the foredome to the actual low tide mark, and then another 450 meters roughly from the low tide mark out to where the wave energy converters will be deployed. And this just is a schematic of roughly how the two different plants work. Again, one wave energy converter is driving an electric plant, another driving a desalination plant. What's missing in this diagram is a link between the electric plant and the desalination plant, because the desal plant does require a small amount of electricity to run the control system, open and close certain of the valves, et cetera. Any excess electricity produced by the Wave 2E system there will be fed back into the Camp Rilea grid. Again, the Wave 2E system is a closed-loop system running on fresh water, and the Wave 2O system is open-loop running on seawater. Has certain challenges to it, which is one of our key pieces we want to prove. So now so that will take place, we hope, in the fourth quarter of 2015, pending our receipt of sufficient financing. Almost immediately after that, we will begin developing our very first commercial project, and that would be on the island of São Vicente in the Cape Verdean archipelago. A couple of interesting facts about Cape Verde. It has the highest cost of water on the African continent. It's roughly $4.50 a cubic meter. Desalination is something that the country is very used to. 85% of all of its water is produced via desalination, but 100% of that 85% is produced using diesel generators. So the country is extremely interested not only in having additional water supplies in a water-scarce environment, but also relieving its dependence on fossil fuels in order to drive these desal systems. And on the island of São Vicente, the main town is Mindelo, and right in the middle of Mindelo is a huge diesel generating plant which is spewing diesel fumes right into the neighborhood next door, and producing fresh water. It's an extremely inefficient system. Interestingly enough, the water situation in Cape Verde has created a class system for water. So if you're one of the wealthy members, you can have water brought to you by pipe and have 24/7 access to water. If you're in the middle class, you can essentially buy water and have it delivered to you by truck and pumped up to a tank on your roof, and depending on how much you have to devote to water, you can have water 24/7 there. However, the poorer people in São Vicente and through much of Cape Verde really only have access to fresh water 2 days a week. So it's quite a social impact associated with that. Another aspect of it is Cape Verde is actually a terrific potential agricultural site, but there's not enough water, essentially, to develop that aspect of the economy. So these are some of the social impacts of water that our system can solve. So this is my last slide, and this is essentially meant to prove effectively that the numbers work in this particular situation, and that using wave power to desalinate water can be a very profitable enterprise. The first thing I need to do is sort of set up what is our business model, and our current business model is basically to sell equipment and services to local investors who set up a special purpose vehicle, and that's exactly why we've set up the subsidiary in South Africa, because we're anticipating quite a bit of business there. But that special purpose vehicle buys the equipment and services from our company, and essentially we go through the early sort of site characterization work with a bunch of subcontractors, et cetera. And essentially it's the SPV that enters into a purchase contract with the off-taker customer. And so that avoids our company having to take, shall we say, risk associated with who the customer is. One other reason why that's a very important business model has to do with the fact that we need to have local partners involved in these projects. Because one of the lessons that we've learned over the years is that if you don't have local partners, it's much more difficult to get the kind of buy-in necessary to get these projects done, and furthermore, to get them financed. But so going through the graph here very quickly, again, on the far right is the orange bar, which basically shows the average cost of water on the entire, 9-island archipelago of Cape Verde. It's roughly $4.50, as I said before. The other bar charts basically add up the costs associated with supplying water to them. And this is based on a 4,000 cubic meter per day plant. In other words, 8 of those 500 cubic meter modules that we will be testing in Oregon. And essentially the capital cost is the far left bar. And that includes operating and maintenance expenses. It includes all of the sort of preliminary project development expenses. And then moving to the right, next we have the EPC margins associated with the group of people that essentially do the engineering, procurement, construction of the project. And then to the right of that is effectively the costs associated with the financing and giving our SPV partners a sufficient margin in order to have it be interesting. And then when you add all that up, it comes up to a water purchase price of $3.50 that we would be selling, or the SPV would be selling water to the off-taker customer. In Cape Verde, it would be Electra, which is the local electric and water utility for most of the islands. At that particular rate, Electra has indicated that they will take all of the water that we could produce at that level. Each of those 4,000 cubic meters per day plants roughly cost $25 million. And in order to fill the gap between supply and demand on the island of São Vicente would take roughly 4 of those plants. So that's $100 million right there just for one of those islands. So it's a fairly big proposition that we're taking on. I think that's pretty much it for that slide. And finally, what I want to stress is, I sort of hinted at it before, that we've set up our company specifically to focus on this market for some good reasons. A, of course, we think that there's some significant profits there. We're solving a very difficult problem around the world. It's a big marketplace potentially. And another reason is that we are through and through a social enterprise. And this really has to get to how we actually build our business going forward. It's helpful in terms of attracting talented people to come work for us. We got a lot of people who are very, very dedicated to the work that we're doing. They think it's very, very important, and it is. But also when it comes to financing our company, which is a very, very difficult problem for technology companies in this marine energy space, we're focused on a particular kind of investor, and we already have some involved with the company who are impact investors. So one of the things that we're very, very concerned with is what is the impact of our particular technology. And so that might seem a little bit strange for a technology development and project development company, but impact is a very, very important aspect of our company. And that's my presentation. Thank you very much.
Yes, okay. Bom dia, good morning. I think I'm supposed to speak in English. I have to use this barbaric language. I'm sorry. Oh, sorry. Good morning, everybody. And first of all, a word of thanks to the organization for this kind invitation. And I'll go straight to my presentation because it seems that we are short of time. And I was warned by the chairman that he had a switch there that would cut my microphone at the appropriate time. So, what's my purpose of the presentation? I come from a R&D institute, research and development, and so my task here is not to talk about a specific solution development, which I appreciate very much. I had the time to listen to this last presentation. Fantastic job, really. I come here to explain what's our work, our potential, our developments, and what we are aiming at, and eventually you will see how this contributes to the global objective that we have. I come from INESC Tech. I will explain brief. How do I move this? Is in this? This is ahead? No. This one? Okay. Thank you. My organization, where can I see this? My organization today, it joins together 3 universities and 1 polytechnic institute. It has around 800 researchers, 300 with PhD degree. So it's, for Portugal, it's fairly large, although in the world stage it's probably just a little flea. But the fact is that we are able to join together a lot of skills, competencies in a number of areas. We run 12 research centers. I don't suppose you, yeah, you can read this. You can see that we have from photonics to computer graphics, to power systems, to critical software, etc. And this is the strength of the organization because we can manage to put together a lot of scientific knowledge and technology knowledge to bring up solutions and not only scientific projects. And that's what we did with, in our activity. We have identified a series of challenges in the society. We can see that we have identified, for instance, challenge from the sea economy, from the health sector, from natural resources and environment, and so on. And we created some initiatives that we call the Tech for More. We'll see the Tech for Sea, the Tech for Health, and so on. And I'm going to talk a little bit about the Tech for Health. Well, sorry, Tech for Sea, about the Tech for Sea, which was aimed at launching a challenge to a number of scientific areas that would drive them to produce something useful to the market. And we have called up from the knowledge of many of our research centers. I must tell, for those that don't know, that we have given our share of contribution to the renewable energy sector in Portugal, namely the wind power sector, where Portugal is #1 in the world, as you know. Perhaps some of you will think, what, #1? Yes, because I discovered the statistics where we could be #1. It's hard, but I hate it to be #2 in terms of percentage of wind energy generation in the portfolio of generation of Portugal. In terms of energy, we are #2 behind Denmark. But I found out that we are #1 in the world in terms of installed capacity divided by the gross domestic product. It's not stupid, actually. It means that it's the country in the world where wind energy has the largest contribution to generating wealth. Right? So after all, it's not a bad statistics. Okay, but frankly, from a small country, I feel very comfortable to say we are #1. Right. So from Tech for Sea is our demonstration that we mean business when we talk about the ocean and the ocean challenges. And so we joined together basically around a core commanded by robotics, control, and navigation. We joined together the capacities from telecommunications, sensors, data mining, serious games. Don't ask me what that is, it will be a long story. Power, trustworthy software. Critical software is mandatory if you go to deep sea. You cannot send just a diver 3,000 meters deep to do some maintenance, right, if there is a bug in the software. So the kind of software that you have to place down must have the same quality, fault tolerance, etc., like aerospace software. So it's this kind of things that change. And we launched Tech4C, and together we invited a very fine group in the University of Algarve to join with us because they had the knowledge on acoustic communications. We have the research center of the Portuguese Navy together in our initiative. We have the Brazil, where I'm the president, INESC Brazil. And we are acting in deep sea, fisheries, aquaculture, safety and security, and environment monitoring. Where is energy and power coming from there? Oh yes, all the technologies that I'm going to talk are, have an application in the energy generation. We have several. We have facilities in several places around Porto, plus in Algarve, and one of them is OCEANUS. How is this going? There. No. This. Yes. This is in the Leixões, the harbor near Porto, where we have. Located OCEANUS, which is a consortium of research institutes devoted to sea economy, and where Tech4C is also deployed. And we have robotics platforms to operate in the ocean, from service vehicles to underwater autonomous vehicles, plus air vehicle. This is an image of our earlier submarine that has been regularly contracted by Águas de Portugal to inspect the quality of the waters offshore in our coast. I don't know if I have the time to make, you'll come and help me later. And this is photo, you can see our autonomous submarine shipped to Brazil to inspect hydropower station reservoirs. So we are exporting these technologies, and for inspection of reservoirs, this machine inspects the dam, the integrity of the dam, the deposition of sediments on the floor of the reservoir, and also the quality of water. And it's, of course, much larger than the first one because it has more missions and it consumes a lot of power. Now, we have laboratories and so on. I have some pictures. That's one of our laboratories for robotics. We are going to talk to you quickly about two things that I need to tell you. One is the Marbed project. We are probably the first, if not one of the first, country in the world to make available to the fishing fleet on the coast, the small vessels that fish sardines, Wi-Fi without satellite or GPRS, etc. And this was a project contracted by a company that owns a fishing fleet. So we developed all the technologies. We have 2 land stations operating. We have the fishing ships equipped with the sea nodes, as we call it. So, and we provide access to internet to the fishing fleet. Up to 10 miles on the coast from the land stations. But each fishing fleet also replicates the signal. So if we have many ships fishing, we extend the network away. So they created on the internet a sort of virtual market. So when they fish, they don't need to put the fish in the market in the harbor. They deliver it directly to the client because over the internet, there was a bidding process, and they already sell the fish there. So now, imagine that we have a wind farm floating, for instance, which is the technology that we need in our coast. This could be used to replicate this Wi-Fi network, to provide a parallel communication link, etc., etc. All floating platforms that we could put on the sea can use our technology for providing cheap, very cheap Wi-Fi communication. These are some photos of the things, on the left, the land station and so on. We have many projects in several domains. I just run quickly because the chairman is waving his hand. Someone in the audience, his friend, I suppose. No? Yeah. Environmental monitoring, lots of projects. In the safety and security, this picture shows a project, actually an European project. This is the demonstration in La Spezia, Italy, of the safety and security. Meaning, this is a robotic catamaran that takes on it, this is a demo only, right? It's not the final product. Takes a robotic buoy that when there's some ships sinking, many people drowning, there is a flying drone that locates where are the people. One of the big ones goes to the middle of it and launches robotic buoys that go and get the drowning people and bring them back. Now, this has been tested in the NATO center in La Spezia, and we hope that next year it will be already a final solution of deploying. We have projects in the deep sea, in aquaculture, fisheries, and so on. I'll just go quickly to the deep sea project because some people in the audience may be Portuguese, and I think they will be interested in knowing this. We are conducting one of the only 6 projects approved by the European Defence Agency out of more than 70 proposals submitted. And this project is actually the construction and operation of a robotic underwater platform for deep sea. So we will be doing the final tests and demonstration at 3,000 meters deep in next May. Within 1 month, we'll begin the tests at shallow waters. And so we will have an autonomous robotic platform with an autonomy of about 3 months that has military interest because it can be camouflaged underwater to surveil the waters. But it has also civilian interests because it can sensors for anything you may think. And so this is Portuguese engineering, okay? Portuguese technology, Portuguese science behind. We are looking very concernedly to our new Amazonia. What's our new Amazonia, Mr. Chairman, do you know? It's a way of winning 1 more minute. It's 4 million square kilometers, 4 million square kilometers, half the size of Brazil, that it's now the continental platform and extension where the sovereignty of Portugal is requested to be recognized at the United Nations. 4 million square kilometers. We are looking at that. So okay, and what else? Here. I end with this. We invite all interested parties in responding to the ocean challenge, including generation of energy, to consider alliance or partnership with this infrastructure that has been recognized by our Ministry of Science and Technology as one of the key top national technological infrastructures, Portuguese. I hope your imagination is, I'm sure your imagination is enough to understand that all technologies linked to communications and robotics and so on are useful also for energy projects in sea, including when we go to deep sea. Thank you very much.
Michael, you have the word.
Many thanks, and it's a great honour to be here today, particularly as I understand this is the first time that the subject of risk and insurance has been addressed at a WavEC seminar. It's a very important area, particularly by the time you start to come to look at financial modelling for projects. But quite often at that stage, it's getting a bit late to optimise what it's going to cost and so on. So what I'm trying to lead you through here today is that journey. Just by way of background, if I may, MDS is the largest insurance broker in Portugal with a considerable expertise in the marine sectors and the energy sectors, amongst others. It's also one of the driving forces behind a major global network of insurance brokers, of which I'm here to represent the UK renewable energy teams. Within that sphere, we have experience ranging from the launching of early-scale devices, both wave and tidal, at test centres, through to the first deployments, through to we're currently working on the first commercial-scale tidal flow project, the Maygen project up in the Pentland Firth, as well as deployments of floating met masts and indeed fixed offshore wind farms in German waters. To share some of those experiences with you today, first of all, I'd like to make the point that the insurance market, if not properly prepared, you will find to be surprisingly risk-averse. Insurers like lots of numbers they can model and play with and define what the variability of them is. If you go to them cold with a risk that they don't understand, that they haven't seen, if you go to them a month before launching a deployment of a wave device to site, you'll find the answer isn't expensive, it's just no, we can't insure you, we don't understand you. As an example, we saw a year or so back the first deployment of a cable at a high tide site in North America, where when the principal went to their insurance broker, which was one of the biggest in the world, asked them to get the insurance for the cabling, they were told, no, it's not possible. You have to prove you can do it first before we're able to get you covered. By contrast, actually, in fact, a local broker with considerable expertise in the area working on behalf of the contractor was able to then go and place the corresponding cover for the contractor in the market. In other words, if you apply the time and effort to understand the risk, develop the story and portray it to insurers, they will start to respond better. Don't just leave it to the last minute. And what we're saying here is we want to move from a slightly scary prototype to something which is getting closer to commoditization, off-the-shelf kind of response. In that light, and using the examples within the renewable sector across the board, in terms of the way the various types of technologies will be approached at the moment, by the time you get to solar PV and even to a large extent onshore wind, it is commoditized. There are challenges, but they're relatively easy to, for most of the risks associated, to be addressed by insurers these days. Where by the time we get to fixed offshore wind, it's starting to get to be a case where there's a reasonably healthy large insurance market for it. The premium rates are starting to settle down at a considerably higher rate than anything onshore for obvious reasons. There is still some variability perhaps in terms of the level of deductibles, self-insured retentions that clients are likely to face in areas where the most problems have been experienced. So particularly, say, cabling, which has represented something like 80% of all losses in offshore wind by number or by quantity. By the time you get to the wave and tidal and floating device sector, what experience has been in the market to date is improving, but at one stage just a couple of years ago where there had been maybe 12, 15 significant size prototypical deployments, those insurers that had been involved in those were looking at having paid out €5 for every €5 in claims for every euro in premiums that they'd received to date. So it's, in the scheme of their overall premium base, it's tiny, and they see it as a learning experience, but it's still quite scary, and we need to build up from that to something that is a more economically sustainable model all round. As a result of that, the rates currently being charged for tidal devices or wave devices are relatively high, assuming you've got the story together in time to get the cover in the first place. That will come down. We're talking, as I say, on the first commercial array, we're having to extrapolate where 2 or 3 years of successful running should take them in terms of insurance rates, and we would expect them to be perhaps even halve over that period compared to where the current rates are. More to the point, as we'll go on to see, there are other factors why the actual sums insured will hopefully come down with replacement costs being reduced over time. How much? It is a scary amount, actually, when you factor it into the financial models. Even with fixed offshore wind, you frequently hear developers referring to their insurance premiums contributing something like 25% of their operating expenses. And that's in a much more mature state than we're looking at with some of the earlier stage technologies. One of the device developers we're working with at a test site, who is grid connected, albeit with a very small prototype, so relatively small output, the revenues generated despite a very high support mechanism for that project are less than the insurance costs currently generated by the requirements under the lease for liability insurance, removal of wreck cover, and so on and so forth. Obviously, that's not a commercial proposition anyway, but we need to try and get the balance there right too. Why is it so expensive? There's a lot of repetition there of track record. It goes back to, if not data, understanding that people have done it before. If the more that's recognizable in your project to the insurers, the easier it will be for them to understand what is going on there. If every single aspect, including particularly the likes of the contractors and the installation methodology, is new and untried, they will be very reluctant to get involved at all. The more you can tick their boxes on that, the better the response will be, the more economical the price will be. And going down a bit, the understanding of what the costs of your vessels, both for installation and subsequent operation, and particularly a subject I'll dwell on a bit further in a moment, in terms of what weather windows, what weather risk you might have, is relevant. In the ordinary construction insurances, they don't cover weather risk per se. That's something I'll come to separately, but they're still exposed to weather risk when it comes to trying to fix something potentially, because they have, if there's a claim insured, they have to pay for the vessel. If the vessel's sitting at port doing nothing, they end up with a much higher cost. So these are important factors to them too, as are how available any replacement parts will be, and particularly how long it might take to replace them. This has a considerable bearing on the ability to generate any cover in respect of loss of profits down the line. And any warranties and guarantees availability from the OEMs is very much taken into account. Obviously, at that stage, we're more talking the more mature technologies before any OEMs are significantly involved in that process. There's also, obviously, many of those are relevant to the specific location that a project is in, or the specific regulatory regime lease applicable to it. All of those have a dramatic impact potentially on the relative cost, particularly with regards to the lease obligations, the like on some of the smaller projects where it can have a disproportionate effect on costs, as can marine warranty surveyors. You will find that before you're allowed any insurance, the insurance will require you, the project developer, to employ a marine warranty surveyor who has the power on your behalf to say that vessel's not fit for purpose, that methodology is not going to work. Sometimes even standing on the deck of the boat saying you can't do it like that, you've got to stop, it's not safe. If this process is left to the last minute, the marine warranty surveyor comes in cold, it's not unknown for them to say, no, you've got to go and find another vessel, in which case you might find there's a year's delay. If, by contrast, you engage with that sort of process a year earlier, you will find actually some of what that marine warranty surveyor has to do on your behalf is work that you know you need to do anyway. So you can make him part of your team, your engineering team, to understand the challenges, particularly in the marine engineering environment. The scope of cover obviously is very much dependent on availability in the first place, and at this stage it varies. Going back to that first slide, by the time you get to a solar panel, you're arguing maybe about whether insurers can guarantee the OEM manufacturers' guarantees on availability and supply. by the time you're looking at the other end of the scale, a wave device, that's not a relevant issue. You're not going to get any cover for machinery breakdown availability until you've proven the model, got the hours in the water. At this stage, it's about they will be looking to see whether they can ensure principally the survivability of the device. I said I'd talk a bit more about weather risk. I'll try and keep it short because this is one of my favorites, so I tend to get a bit carried away. This is a specific example that we've drawn together with some partners of an analysis of a project. It's an offshore cable lay specifically, where we've looked at the exposure to wind speed and wave height. And using, on the one hand, synthetic hourly data going back for 23 years for each of those, which is available from a number of sources, mainly the likes of the Met Office, Meteo Group, and the like. You can layer that onto a complex project management tool, and what it essentially does, it looks back and sees if you start on this date with this set of parameters for your work package, this is how long it would have taken for each of the 23 years. So it then builds up, as a result of that, a probability curve of how long that work package is going to take. So you've got there the difference between the left side and the right side is 3 months. And just picking a number, for 90%, the P90 level, 1 year in 10, if you start on the 17th of June, you'll have 6.6 days expected overrun or more. Whereas if you start 3 months later, that same P90 level is 52.9 days. And that's only a 1 in 10 year possibility of that sort of difference occurring with that sort of delay. Furthermore, these green lines represent the variance, the difference to a 5 or 10% level of confidence if you have those parameters wrong. So it shows you, again, how much more exposed that later period is to the fact that actually your significant wave height parameter should have been half a meter lower or whatever it might be. There's some real risk there. Now, to me, apart from the fact you can insure now with certain specialist insurers delays above, say, the P80 level, something like that, to take the significant sting out of the tail. But to me, this is a practice that should be started to look at from the consenting and contracting stage, so people understand what they're taking on by way of exposure, what they're allocating to contracting partners, and so on and so forth. In addition to understanding weather risks, generally speaking, what we're looking at here is probably the sort of things that are already going on to a large extent. It's understanding how to achieve survivability, how to achieve confidence level, minimize the amount of components you have to design yourself. You can bring in more off-the-shelf components wherever possible. Understanding who you're sharing risk with and how to pass it on, using local marine experts, and indeed getting the right support from the risk management and insurance sector at an early stage to help walk through all this and to help actually describe the process to insurers and keep them engaged in that process through the development stage. So possibly even with the case of the Maygen project, we've been keeping the insurers we expect to involve in that regularly updated, probably every 3 months or so, for a period of more than 18 months before the actual start of any project work. This is going forward. Where do we want to take things? Again, these are familiar stories. You're going to want to reduce the cost of your technology in order to get the capex down in the first place. But by getting the capex down, that reduces the cost to any insurers of any claims. Therefore, the insurance premium comes down by necessity. The more you can use methodologies and moorings and designs that are understood and proven, or you're collaborating with other partners, the more likely it is that they will be recognized by insurers, they'll understand, and they'll start to take it as standard. O&M efficiencies, just as an example from...
I'm sorry to interrupt you. If you, when possible, if you can prepare a talk.
Certainly, sorry, apologies. Just quickly on that, certainly there's the ability to create in-house expertise to reduce repair costs and the like. And then the final leap was essentially saying, what does it look like in terms of how close to commoditization can we get? What will it look like? Again, it's harping on those same topics. It's as in the sea, getting data insurers, better understanding of some of the problems in terms of cabling and working with an experienced team, including on the marine warranty surveying and risk management side, that understands the issues. As I say, most of those stories are not necessarily dramatically a surprise to any of you, I'm sure, but the key message of all that is the more you can think as early as possible how to engage with the insurance market so that the right broker, etc., can work with you to explain that story to the insurers and to prepare the ground for your future deployments. The earlier you can address that, the better.
Michael.
Thank you.